Hello everyone and welcome to this new video about abstract algebra, and today we're going to talk about properties of isomorphisms. So let's start by proving this result. We have an isomorphism phi between a group G to a group G bar. Then phi maps the identity of G to the identity of G bar. So let's prove it. This is fairly simple to prove. So notice that since for any A in G, we have that A times E is equal to phi times A times phi times E. Okay, but this is equal to phi times A, since E is the identity in G, and so from this we deduce that phi times A times phi times E is equal to phi times A, and then obviously multiplying E on the left, we get that phi times E times phi times A is equal to phi times A. But there's exactly one element that does this in G bar, and this is the identity. So we have proven that identities gets mapped to identities. Now let's prove another fact, and that is that given an element A in G, we have that if we raise to the nth power in G bar the image of A under phi, then we get that this is just phi of A to the n. So again, this is very simple. All we have to do is basically apply mathematical induction to this property of isomorphisms. Let's see how we can do that. So first of all, notice that for the base case, it is true that phi of A squared will be equal to phi of A times phi of A, which is just phi of A all squared. So the base case is checked. So now for the induction hypothesis, we're going to suppose that for a general n is equal to m, phi of am is equal to phi of A to the m. And then we're gonna, as the induction step, we're just gonna show that phi of A n plus 1 is equal to basically phi of A to the m plus 1. So how can we do that? That is very simple. All we have to do is write A to the m plus 1 as A to the m times A, but using the induction hypothesis and also using the properties of isomorphism, we can write all of this as such. And then again, using the induction step, this is this member here is just phi of A to the m, and then all of this will be multiplied by phi of A, but this is just phi of A all to the m plus 1, and so we have completed the proof. So in general, for n in the positive integers, we have shown that this identity holds. For n is equal to 0, this is tackled by the previous fact, because we're going to have that A to the n is going to be the identity, and then obviously if we have phi of A to the n, in this case n is 0, this is also going to be the identity, but in the group G bar. And so for n is equal to 0, this is also checked. Now all we have to do is check that this holds in general. But to check that this holds in general is fairly simple as well. So to check that it holds in general, now we only have to tackle the case where n is less than 0. But if n is less than 0, then minus n is greater than 1. So what we can do is, again, take an element A, or A to the n, and then we're going to multiply it by its inverse in G. This is going to be equal to phi of the identity, which is the identity in G bar. But this can be written as phi of A to the n times phi of A to the minus n. And so applying the result we proved for positive integers, since minus n is a positive integer, we can write all this as phi to the A to the n times phi of A to the minus n. And so now by the transitive property, we have that phi of A to the n times phi of A all to the minus n is equal to E bar. But this implies that phi of A to the n is equal to phi of A all to the n. And so this completes the proof of the theorem. Now let's prove some other facts about groups. So the next one is also pretty important, and it basically states that if a group is cyclic, so if we have the G is cyclic, can be written as the cyclic subgroup generated by A, then we're going to have that G bar can be written as this group here. So to show this, all we have to do is to show that all elements of G bar can be written as powers of phi to the A. So let's suppose that G is in G bar, actually small g bar is in G bar, well then, since our isomorphism phi is by hypothesis a surjective function, it will exist a small g in G such that phi of G is equal to G bar to small g bar. Okay, but our small g, since it's an element of A, it will be written as a power of L, of A. So I'm gonna say A to the L, where L is an integer. But we have seen that this is equal to phi of A all to the L. And so we have reached this point here, where by transitive property of equivalence relations, we're gonna have that G small g bar is equal to phi of A to the L. So it can actually be written in this form here. So what we get is that G bar is a subset of this as a set of this set here. But notice also that by closure, since phi of A is an element of G bar, this also is a subset of G bar. And so from this it follows that G bar is precisely a cyclic subgroup and it's generated by phi of A. And so this proves this fact. Another very important fact is that isomorphisms preserve orders. This means that if we have A in G, then the order of A in G will be equal to the order of phi of A in G bar. So again, let's prove this. And this is fairly simple. So suppose A of n has order n. What that implies is that A of n is equal to the identity. Okay, but then phi of A to the n is going to be equal to phi of A all to the n. But this is going to be equal to phi of the identity, and this necessarily then has to be equal to the identity in G bar. And so from this, it actually follows that the order of phi of A is also n. And now I'm going to prove another important fact that will basically be the basis for the fact that if two groups are isomorphic and one of them is abelian, then both are abelian basically. And that is, if we have elements A and B in G, and we have that in G they commute, well then this will be true if and only if phi of A and phi of B in G bar commute. So let's prove this again. So if A times B is equal to B times A, then we're going to have this equality. So phi of A times B is equal to phi of B times A. But this is equal to phi times A times phi times B, and this is equal to phi times B times phi times A. But by the way, we're proving the this direction first, so the forward direction. And well, here we have reached the result already. So now we have to prove the reverse direction. For the reverse direction, what we're going to do is going to suppose that this is true, so that phi of B and phi of A commute. Well, but then what we're going to have by the properties of isomorphism is that phi of A times B is going to be equal to phi of B times A. But since isomorphism is a bijective function, then we're going to have that A times B is equal to B times A, and so this proves the fact. So these properties are quite important properties of isomorphisms, but they're not very useful when it comes to actually proving that two groups are not isomorphic, because these properties, we could call them local. As you can see, we reasoned in terms of elements of groups. These local properties, however, have some global consequences, and we're going to state them in a theorem. We're not going to prove it super in depth because it's literally a super easy corollary, and it actually follows directly from these things. So we're going to just state them, and that is, let's say, global properties of isomorphisms. And now we're going to list them. And so these are all the most important properties that some of them follow immediately from the previous facts, and we're actually going to prove some of them. So I'm going to highlight the ones that follow immediately from the facts we proved earlier. In particular, from this fact here, this property here follows immediately from that. You can see why that is the case. And also this property here follows from the properties that we proved about orders of elements, etc. And so this property here also follows from what we said about what isomorphisms do to elements that commute. And well, what we're going to prove is going to prove just some of these facts. In particular, we're going to prove this fact here, 4 and 6, which is basically isomorphisms map both in reverse and forwards, subgroups to subgroups. And also we're going to prove, well, I mean, you can see why this is very simply the case, because that is because isomorphisms are bijections, and so of course the cardinalities or actually the order of the group is going to be equal. So we're not going to prove this, but we're going to prove this. So we're going to prove this, and actually just this one, because then the reasoning for this one is the same, and then we're going to prove also this one. So I'm going to start by the first one, and well, so we have an isomorphism from G to G bar. So then this is a bijection, so there exists an inverse function, a set theoretic, we could say inverse function, that basically is defined as mapping an element y of G bar to an element x of G, such that phi of x is equal to y. Okay, but now what we want to prove is that that phi to the minus 1 is a bijection. Is basically, we already know this from, well, a lot of properties of functions. And so all we have to do is that given y and y prime in G bar, phi to the minus 1 of y times y prime is going to be equal to phi to the minus 1 of y times phi to the minus 1 of y prime. So this is all we have to show basically. Okay, so let's see. Phi to the minus 1 of y prime will be mapped to an element x tilde of G bar, and this element x tilde is going to be equal to y prime. Okay, but if we suppose that phi to the minus 1 of y is equal to x prime, and phi to the minus 1 of y prime is equal to x, actually this to x and this to x prime, then we're going to notice that this is going to be equal to phi of x times phi of x prime, which is equal to phi of x times x prime. And so from this, it follows that x tilde is equal to x times x prime. So in the end, phi to the minus 1 of y times y prime is going to be equal to x times x prime. But this is precisely phi to the minus 1 of y times phi to the minus 1 of y prime. And so this proves this first fact about isomorphisms. So for this second fact about subgroups, now we're going to prove property number 4. And well, what this says is that suppose we have a subgroup of G, we're going to call K, and now what we want to see is what phi does to this subgroup. So by hypothesis, since this is a subgroup, it satisfies the one-step subgroup property, and that is for all A, B in K, A times phi to the minus 1 is in K. Let's remember how we define phi of K. That is the set phi of small k, with small k coming from big K. And well, what we want to show is that this is a subgroup. So we're gonna take two elements. I'm gonna call them like A tilde and B tilde inside of phi of K. And well, we notice that we can write A tilde, since phi is a isomorphism, you can write it as a phi of some value A, actually A prime, and B tilde as some phi of B prime. Okay, but A prime and B prime, by the definition of phi of K, are going to be members of K. And well, then we have that A prime times B prime to the minus 1 is going to be equal, is going to be an element of K by the one-step subgroup test. And well, then what we have is that in the same way, phi of A prime times B prime to the minus 1, which is phi of A prime times phi of B prime all to the minus 1, is going to be an element of phi of K. Why is that? Because this is an element of K, and by how phi of K is defined, basically elements of K are mapped to phi of K. And so, but notice that this is precisely A tilde, and this is precisely B tilde. So what we have is that in the end, A tilde times B tilde to the minus 1 is an element of phi of K. And so phi of K is a subgroup. And the proof in this case here is basically the same, but reversed. And now let's prove that isomorphisms are an equivalence relation. And so recall, an equivalence relation is a relation which has the following properties. So we're going to call a relation, we're going to call it tilde, is an equivalence relation if and only if So as a first property, it is, we call it reflexive, meaning that every element is equal to each other under this relation. Then it is symmetric, and then it is transitive. So these properties hold basically. So I'm going to show that, actually this is an if only if. Okay, and so now let's prove that this holds in terms of groups. Actually, in terms of isomorphisms for groups. So for the first one, we're going to construct the isomorphism that shows that all groups are isomorphic to themselves. And this isomorphism is the identity. And you can quickly see what this is an isomorphism. This is trivially a bijection. And well, it is also an isomorphism because since it maps basically elements to itself, then this is trivially, it also preserves the group operation. So this shows that for all groups G will be isomorphic to itself. For the symmetric, on the other hand, for the symmetric property, I'm going to suppose that G is basically isomorphic to G bar. Okay, but then we have a map G from a map phi from G to G bar, such that this map is an isomorphism, and it is basically bijective, and it satisfies this property for all x and y in G. Okay, but now what we're going to show is that, well, by what we've shown earlier, that is that the inverse function, so the inverse of this is an isomorphism. We're going to have that phi to the minus 1 is an isomorphism between G bar and G. So this implies that G bar is isomorphic to G. So this actually already proves the symmetric property, and for the transitive property, we're going to suppose that G is isomorphic to G bar, and G bar is isomorphic to G tilde. So what we have in the end is an isomorphism G from G to G bar, and an isomorphism psi from G bar to G tilde. Then the way in which we're going to achieve the isomorphism is by composing them. And so what we're going to get in the end is a map from G to G tilde. And so actually we're going to prove in general, and I'm going to say that it is proved, but we're going to prove it now. We're going to prove in general that compositions of isomorphisms are again isomorphisms. So this is a pretty important fact, so we're going to prove it on its own, because I forgot to mention it before, so I'm going to prove it. So let's again suppose that phi is in the same framework as before, a isomorphism from G to G bar, and psi is an isomorphism from G bar to G tilde. Well, then what we want to prove is that, what we want to show is that psi composed with phi is an isomorphism. So how can we do that? First of all, we're going to notice that first we're going to start by proving injectivity, and we'll define this. But this is pretty simple, because if we have x and y in G such that x is equal to y, well then this is true if and only if phi of x is equal to phi of y. And why is that? Well, because the if and only if comes from both well-definedness and injectivity. But notice that these are elements of G tilde, and if two elements of G tilde are equal, well then this is true if and only if under psi they're equal. Again, this is because psi is both well-defined and injective. Sorry, here should be y. And so we have reached what we wanted to show. In particular, we reached the point that we proved that this composition is injective. So to prove that it's surjective, we're going to take a y in G tilde, and then by the surjectivity of psi, we're going to find a, actually we're going to call it y prime in G bar, such that psi of y bar is equal to y. But then by the surjectivity of phi, we're going to find a y double prime in G, such that phi of y double prime is equal to y prime. And so in the end, we get that psi of phi of y double prime is equal to y. And so this proves also that this composition is surjective. So now all we have to show is that psi composed with phi of x times y is equal to psi composed with phi of x times C composed with phi of y. So how can we prove this? This is again very simple. Let's recall the definition of this thing here, which is just C of phi of x times y. But by applying the properties of this isomorphism phi, which is an isomorphism by hypothesis, this is going to be phi of x times phi of y. Okay, but again, applying the properties of the isomorphism psi, this is going to be equal to psi of e of x times psi of phi of y. And now we have reached the point, we have actually already reached this equation. And so from this, we have proven that, the fact that we want to prove. In particular, we have proven that composition of isomorphisms of groups are isomorphisms again. So actually the third, I would say the third property in order to make an isomorphism an equivalence relation actually followed from this fact. So with this said, I think in this video we have actually proven a good amount of properties about isomorphisms, and I mean the reasons why these properties are very important, and I already mentioned it, but I'm gonna mention it again right now, because maybe in the next video we're gonna first prove Cauchy's theorem, and then we're gonna make some examples to show how we can actually show that some groups are not isomorphic. So these properties come really in handy when we want to when we want to prove that two groups are not isomorphic, because in order to prove that two groups are isomorphic, we just have to construct an isomorphism. But in order to prove that two groups are not isomorphic, we actually have to notice some properties that we could say some properties that don't match. So for example, if we have, well, of course, if we have two groups that have different cardinalities as sets, we're gonna immediately say that they're not isomorphic because we cannot construct a bijection. But imagine that we have two groups that, for example, one is cyclic and the other is not. Well, one is abelian and the other is not. Well, now we can immediately say that they're not isomorphic because we proved these properties. And actually, if it's not super clear what that is the case, remember when we introduced isomorphism, we said that isomorphisms are algebraic equalities. And so this is why actually isomorphisms are constructed in such a way that they basically preserve these algebraic properties about spaces, about groups. And so this is why if one group is, for example, if you have an isomorphism between groups and one is cyclic, then the other must be cyclic as well. That's because they preserve these kind of properties. And so now we can say when two groups are not isomorphic. So if one is abelian, the other is not, we're gonna know that they're not isomorphic. If one is cyclic and one is not, they're not gonna be isomorphic. And now we also can see if two groups are not isomorphic based on the number of elements of a certain order, because of this fact that we prove here about orders. And we can also prove that two groups are not isomorphic based on the numbers of a certain order, because we've proven that basically isomorphisms preserve orders. What that implies is that two groups that are isomorphic have basically the same number, or they have to have the same number of elements of every order. So with this said, I'll conclude this video here.